Now we can generalize that last result. If we have a point P in a plane, we can find the distance from the point P to the plane by simply finding any point on the plane and I think I've violated my margin here, any point on the plane, and we find a vector from P to that point, or from that point to P, it doesn't really matter. So we find this vector, messed up the head of that vector, but you can see what I mean, and we project that onto a vector normal to the plane. So let's use a different color for the normal vector. Let's just say that we have a vector here that's normal to the plane, meaning that any line in the plane is going to be perpendicular to this normal vector. Whatever line you choose will lie at a right angle with the normal vector. Okay, so we have any point on the plane, we have our normal vector, and our distance is just the projection of this vector, which I should probably name. Let's let this point be Q. And this point is P. So the distance is very easily found. It's just the projection onto N of the vector PQ. And we'll do the magnitude of that because, as we've seen, the dot product might come out to be negative. So that's it. Now, if we put coordinates on the point P and coordinates x0, y0, z0, let's say on the point Q. So if the point P is x, y, z, and Q is x0, y0, z0, any point on the plane, then what we're saying, and if n is ai plus bj plus ck, then our vector pq is x minus x0 I plus y minus y0 j plus z minus z0 k. Now actually I've done that wrong because I've gone from x, y, z to x0, y0, z0, and I'm doing the vector p in this direction, and the vector pq is actually in the opposite direction, but I'm not going to correct that here. I could put a parenthesis around this and put a negative sign in front of it, and maybe I'd better do that just to make sure I'm not telling a lie. But it doesn't matter whether we project the vector from here to here or the vector from here to here onto n, since we're taking the absolute value. Okay, and sorry for that little digression, but now we have PQ equal to this and our normal vector equal to this, so that the projection onto n of PQ, which would correspond to the component of this vector or this vector in the direction of n, is equal to PQ, and let's put magnitude here, PQ dot n divided by the magnitude of n, remembering that n divided by the magnitude of n is just a unit vector in the direction of the normal vector. PQ dot n is magnitude of PQ times magnitude of n times the cosine of theta. So that equals magnitude of PQ times the magnitude of the cosine of theta. Equals going to switch to a Sharpie here. X minus x naught I plus y minus y naught j plus z minus z naught k, and I'm sure you know where this is heading. It's really sort of unnecessary to write this out, but there's a point that I want to make about formulas versus pictures. So we dot the two vectors, divide by the magnitude of n, which is just the square root of a squared plus b squared plus c squared. Okay, and this then equals the quantity a times x minus x naught plus b times y minus y naught plus c times z minus z naught. That quantity divided by the square root of a squared plus b squared plus c squared. Now, this is a handy formula for the distance between the point P and the plane, and that's a formula you could memorize, but it's much easier to simply understand this picture and write out the meaning of the picture. And this formula would be a bear to remember, but it's not difficult to visualize.